对，那我们时间差不多了哈，我们现在开始吧。对，欢迎大家来到我们本期这个 Web3BuidlerTech 的技术专题分享。那我们今天邀请到的是 QED 的创始人兼 CEO Carter，他会给我们带来关于 BTC 生态的分享，BTC 应用的未来之开发者指南。Hello everyone, welcome to this week's deep diving session. We invited QED's founder and CEO Carter. He will give us a talk about the future of Bitcoin application, a developer's guide. Yeah, welcome Carter. So yeah, you can start.
Okay, yeah, thanks for the introduction and thanks for having us today. So super excited to get into some of the nitty-gritty details of getting started building on Bitcoin and also talking about some of the future prospects for the Bitcoin execution layer. Let me just share my screen and we can get into it. Okay, so hopefully everyone can see. Whoops, let me just close WeChat. There we go.
Yep.
So hopefully everyone can see my screen okay?
Yes, yeah.
Great. Okay, awesome. Yeah, so today we're going to be talking about Bitcoin, developers, and the future of development on Bitcoin. So just a little brief introduction about me so you know who I am. So I'm Carter. I'm the founder and CEO of QED. My previous sort of background comes from the more traditional security industry. So I was a black hat hacker as a teenager and then became a white hat, working on lots of cool reverse engineering and security related projects. I also entered the blockchain space a little bit ago. I was the founder of Rapid, which was a proof of stake block producer, and we processed over 160 million unique transactions in production. So yeah, we know our team knows how to build systems that are resilient and that are always working. And as I mentioned, I'm the founder of QED. But let's get into Bitcoin. So there's a lot of I guess, issues or like different blockers to people getting started with Bitcoin development. There's not really a good scripting IDE to get started writing like UTXO scripts, specifically tap scripts. Now that we do have tap scripts, there's not really any ways that we can do code reuse or like organizing code. And this has to do a little bit with the way that Bitcoin VM works as a whole, since we essentially don't have branches, or we can't jump to different positions in the code. And there's not really any good tooling that makes it nice and easy to test out tap scripts. In addition, like spinning up a local testnet, even to get started building is quite difficult. And it's even harder to really use. And then not to mention, there's a lot of opcodes that have been disabled throughout the history of Bitcoin, which means that Bitcoin's VM doesn't even support simple useful operations like, multiplying two numbers together. And this all kind of amounts to a really bad developer UX, which is why we don't really see too much Bitcoin innovation until quite recently. But yeah, so to solve these issues at QED, now QED is a layer 2 on Bitcoin, but we want to support the entire Bitcoin ecosystem, and the solution we came up with is called BitIDE. So it's a full TapScript IDE. It lets you define custom opcodes. So like, let's say I want to, define an opcode which, let's say, swaps two numbers if a given item on the stack is a 1 or a 0, right? I can make a custom opcode, or this, like, you can think of it as kind of like a custom function that can be reused throughout your code. And that's really, really powerful because it lets you, define more complicated operations and be able to reuse code. In addition, we have a full visual debugger, so we'll see that in a little bit. But it just makes it really nice for new guys coming into the Bitcoin development space to test out the VM, start experimenting, start scripting. And if you do make a script that has a bug, to find those bugs very quickly. We also have tag-based stack management, which means that you don't really have to, even though you're still coding in assembly, you don't have to worry about like managing the stack yourself. And we'll show how that works in a second. It also has a built-in local testnet and block explorer, and it's really, really easy to use and set up. And in fact, we're going to do that right now. So to get started with BitIDE, if anyone here is following along, you can just run a single Docker command, and that boots up BitIDE, a local testnet, so a local reg testnet, And it also boots up a block explorer that you can access at localhost 1337/explorer. So it's fully featured block explorer, fully featured IDE, and fully featured testnet, all with a one-line command, which is super nice. So let's do it. Let's go ahead and make a Bitcoin script with BitIDE. So I can just go Docker run, and then we'll see in a second. Okay, so now we have a brand new local testnet set up, and block explorer, and of course BitIDE. So let's go ahead and do it. So first of all, we can see we have an IDE here. In addition, we have a nice block explorer, and we've pre-mined some Bitcoin so that we can access our tap scripts really easily. And yeah, so let's get into BitIDE. So first of all, for like anyone who's familiar with Bitcoin, we know that we don't have things like multiplication, right? But here we have a script that uses some custom opcodes like op split U30, optimal U15 high low to multiply two numbers together. So let's see like if this does in fact work. So if we multiply these numbers in the console together times this number, we get this number, and then we have to remember that right now it's representing these numbers using U15s, so that's a 15-bit integer. So, and then we multiply two of these, like 2x U15, so we have a 30-bit number times a 30-bit number. What's the output going to be? A 60-bit number, right? So if I go ahead and take this number, shift it over by 30 bits, we get 867938. That looks right. And then, of course, if we do this and 1n 30n minus 1n, we get the lower portion, which is in fact correct, right? So how does this all work? Well, let's look a little bit more closely. So over here, this just shows how we can manipulate stack items. So you can see that I tag these numbers here. Maybe we can get into something. Let's just make a new script to show it off. So if I make a new script, I can call it, I don't know, test.js, and I can use some of these opcodes. So let's say I want to, I don't know, break a constant like the number 1337 into bits. I can do b.op num to bits. Let's say I do num to bits 15. And we run it, we can get the bits of this 1337 number. So the way that we achieve this, again, is by using existing opcodes that are already enabled on Bitcoin. So nothing non-standard, everything here works normally on Bitcoin Core. In addition, we can have these locking scripts. So here we have a locking scripts that requires you to multiply two numbers together, or to provide two numbers that multiply to this constant number that's in the script. So, if you want to get started with Bitcoin, you're going to need to create a UTXO, and we can go ahead and do that just by clicking compile UTXO. And then we have a tap script address. So if we click it, we can see it in the Explorer. I can then send some funds automatically to the script. So if I click fund via RPC, it's going to be sending that one BTC over there. So if we refresh, sometimes it takes a second to index. There we go, we found it. And now, since we provided that example script or that example witness over here, we can just go ahead and pull that in for testing purposes and click unlock to run the full tap script transaction. Now, if we go ahead and let's say I want to, let's say we put in some other numbers. So in this case, we have this example witness. If I put in numbers that don't multiply to that result, right? If I put in, I don't know, like 11111 there, and I click unlock, it's going to fail. So it says mandatory script verify fail, script evaluated, right? There's like a non-zero or false element on the stack, which is that equality check, right? But if I, let's say, change it up, fund via RPC, check for UTXOs, let's look at that example witness. So these two numbers should multiply to the result, right? However, if I multiply 1337 by 2 times 2, we get this. So I should be able to divide the other one by 2 as well and still be able to unlock it. And if we click unlock, we'll see that it in fact does succeed, right? So super, super easy to get started with Bitcoin development using BitIDE. Again, like we make all of the sort of nastiness go away with Bitcoin. Oops. And yeah, it's just a really great way to get started. In addition, if you want a fully Bitcoin compatible script, we can take, for instance, this code, which calculates the first like 20 Fibonacci numbers. And we can compile, so we can see the result over here. And we can also see the compiled result, which is just going to take our JavaScript code and compile it into normal Bitcoin VM script. So you can do meta scripting. We can create a custom opcode. Like, let's say, I don't know, I want to create a custom opcode that multiplies a number by 2, right? Well, we can just say opmul, or let's call it opdouble, right? Dot bottom. And then I can just say, well, if we want to multiply a number by 2, we just do opdupe, which is going to take the top item on the stack and make a copy of it. And then opadd, which is going to take that copy and add it to itself. So what's another way of multiplying a number by 2? Well, you add the number to itself, right? So that's what we're doing here. So then if I go back over here and I put in the constant, I don't know, 1 through 7, and then I do b.op mul, or what do we call it? Opdouble, right? It should give us 2 times that number, 2674. And we can see that in the compiled result, it's gone ahead and did that. Now, let's say I want to multiply by 4, or let's say I want to multiply by, I don't know, like we want to do a left shift by, let's say 5. So I is less than 5, I plus plus. We just go ahead and opdouble away. We can see that it handles it there very nicely. And if we, in fact, look at 1 through 7 shifted 5 places over, we get the correct answer. So we've seen this way where we can do these bit shifts left, which allows us to multiply numbers by, powers of 2, right? But let's look in a little bit more deeply back in our slideshow. So again, like one of the main sort of pain points that we have with Bitcoin, again, is just that there's so many disabled opcodes, which makes it hard to build useful Bitcoin scripts, right? Now, let's say if we wanted to multiply 2 numbers without opmul, let's say we have 2 8-bit numbers, x and y, and we want to compute x times y. We could just put x. Ideally, we would like to put x and y on the stack and use opmul, but since we don't have opmul, we have to figure out a way to use opadd to replicate the behavior. And of course, if we can express, if x and y are 8-bit numbers, we can express it as like a sum across the powers of 2, terminating in 2 to the 7. So like I can take any 8-bit number and represent it as a sum over here, like we see with this x expression. And because of this, we can rewrite x times y as this sum of like individual bits multiplied by y times powers of 2. And as we just showed in our example, we actually know how to multiply a number by a power of 2, right? Because we can do the opdupe opadd trick. And because of this, since b sub n are 0, 1, we can just use an if-else branch to like actually do that addition. So essentially, if the bit is a 1, then we add y times 2 to the n, where n is the nth bit, right? And if it's not, then we just leave the result alone. So we actually just showed how to compute 2 to the n, y times 2 to the n, right? So, as I mentioned, to multiply a number by 2 on Bitcoin, you just opdupe, opadd. To multiply a number by 4, we do opdupe, opadd, opdupe, opadd, right? And so on and so forth. You can see by 8. So we're going to need log base 2 of the number we want to multiply and do that many opdupe, opadd expressions for constant multiplication, right? So yeah, like now we know how to do it. Let's implement our multiplication, right? But yeah, we still have an issue, which is that we need to calculate this b sub n value for a given number, right? And we're gonna have to do that in script unless we're multiplying 2 constant numbers, which wouldn't make sense anyways, right? So the way that we can do that with Bitcoin without like op-l shift or op-right shift is we can check if a number is greater than or equal to 2 to the n. So let's say you have an 8-bit number. I'll check if the number is greater than or equal to 2 to the 7, 2 raised to the power of 7. And if so, I then subtract 2 to the power of 7 from the number. And this essentially clears out the top bit. And then as long as I, preserve that result from before where I checked to see if it was greater than or equal to 2 to the 7, that result, like that 0 or 1, depending on that like Boolean condition, is actually going to be the top bit of the number itself. So we've found what the top bit of the number is, and we've cleared it out, which just means that we can continue this process until, we hit all of the bits, because then we can check 2 to the 6 and 2 to the 5th and 2 to the 4th and 2 to the 3rd and 2 to the 2. And then once we have 2 to the 2, we do 2 to the 1. And then for 2 to the 0, that's just our, last bit within the number. So we can just continue this process as we showed with our op split bits to break apart any 31-bit number with existing Bitcoin opcodes. So we don't need special opcodes or new opcodes to be added. We don't need opcat. We don't need anything. It works today on Bitcoin Core. So let's go ahead and just look at that code real quick. And again, this is just a very brief summary of some of the cool stuff you can do. But if we look at op num to bits, the way that it works is we duplicate the item on the stack. Then we see if like the number is less than like 2 to the n, which is, we can, also write it as 1 shifted over I places. And if so, then we mark the bit as a 0. Otherwise, we mark the bit as a 1, and we subtract, again, that 2 to the n value from the number. So we clear out that bit. And then we just keep doing this, n number of times until we've done the full like bit decomposition of the number. But, using these, this may seem like a little bit of trivial stuff. Like, okay, we can multiply numbers on Bitcoin. So what, right? Well, if you extend these principles further, you'll find that, in fact, we can do much, much more complicated things. Like, for instance, here is Blake3, the Blake3 hash function implemented in pure, Bitcoin compatible script. So if we click run, we can see the stack trace. In fact, if we go over to SHA-256, we can see that we've implemented SHA-256, which can be used to verify, multiple or hash multiple items on the stack without using the opcat instruction. So over here, if we click run the script, we can see that like the computed result is as expected. If I don't know, like go over here and do node crypto.random bytes, let's do, I don't know, 48, since SHA's pre-image size isn't that big. If we first go to SHA-256 online, let's go ahead and see what we want to get. So the number we should be looking for is a C68, right? So if it works, that's what our result should be. So if we go ahead and go back to BitIDE, I put that number there. If I go return here, we'll see this is that hex value decomposed as like U32s, where each U32 has one stack item for the top bit and then another stack item for the lower 31 bits. Yeah, so we have a bunch of these items in the stack. We don't need opcat. And if we want to calculate the SHA-256 of it, we just click, run script. It computes it. And again, at the end, what we see on the stack is the U32-bit representation of the, the resulting hash. So over here, these 1s and 0s are the top bits of the hash. And then like, these larger numbers are the lower 31 bits, right? So if we look at like, for instance, this bottom item, if I go over here and we do, I don't know, .to string 16, we can see that this is in fact those bits of, or those, that lower U31 of the hash. So yeah, you can verify Merkle proofs using these techniques. In fact, internally, we've used it to verify Groth 16 proof on Bitcoin. And just to show you guys that this does, in fact, like work really on Bitcoin, if we look at our locking script, which is just the previous script, plus this like this n bit, which just, checks to make sure that it matches a given hash. We can see that it's returning a 1, which means it was successful. If I modify the pre-image a bit, then it's going to fail, right? So if we go over here to our TapScript runner, in fact, we also have one for Blake3 just to show off. So same deal. If I modify one of them, it's going to fail. And then I go over here. Let's say we want to allow, oops, got too many of them. Might have to tweak the UI though. If we click compile and let's say we fund this, And then let's maybe use Blake 3. Oops. And then if we check for UTXOs, we can use that example witness. So here's that that input hex decomposed into its U32/U31 decomposition. And if we click unlock, oops, we need to add more funds. Sorry, let me just. If we compile, it's a large witness, yeah. Check for UTXOs. And let's make this, I don't know, 90K sats. And click unlock this time. We can see that it is in fact unlocked and transferred the BTC to the correct party. So if we scroll down, it's a big one. We see that pay to Taproot output there. So yeah, so if you want to build on Bitcoin L1 directly, like BitIDE is definitely the best tool to get started with. Again, we just installed it from scratch with a single one-liner, get a nice testnet, Explorer, IDE that lets you do code organization projects, the works. You can also like just, directly, if we don't want to use this local testnet, I can use BTC mainnet or the BTC official testnet. We're already actually set up for using the Blockstream APIs for both of those. So it just works like I just showed, except there's no fund via RPC button. So you have to send the money from your own wallet. But other than that, like, same flow. So yeah, that's BitIDE. So for layer 1 builders that want to build directly in Tap scripts or in Bitcoin scripts, check out BitIDE. Now let's head back to the PowerPoint and we can see about, I guess, more of the application layer, different use cases. So if you want to build a protocol on top of Bitcoin with more complex features like smart contracts, then BitIDE isn't the place to go. In fact, you should check out the L2O consortium. So L2O consortium is essentially one of the industry consortiums that ourselves and a few other layer 2s that are planning on deploying on Bitcoin have developed to give a comprehensive set of standards that allow for trustless applications and layer 2s to be built on Bitcoin for the first time that are fully trustless. So everything ZK. But yeah, with L2OA, it just makes it really easy to take any like ZK rollup that eventually yields something like a Groth16 proof or another succinct ZKP to be a layer 2 on Bitcoin. And also, all those layer 2s are interoperable, as we'll see. So yeah, so it's an ordinals-based solution. Essentially, you have a ZKP in each ordinal that you publish, and they're verified by BTC indexer, so they inherit the same security of BTC itself, as in how do we, check what the current state of Bitcoin is? Well, the way to check it fully trustlessly is I boot up a Bitcoin full node and I replay all the transactions and then see what the current block hash is, right? That's how I run a Bitcoin node and check the current state of Bitcoin. Well, if you have the indexer installed for L2O, it also will tell you all of the current state roots for every single L2O blockchain. Again, just by replaying all of the Bitcoin blocks. Of course, main idea here just being that there's $900 billion of money just basically sitting on Bitcoin as it stands and not being used for DeFi or any other purposes. So yeah, L2 is a great way if you're building a protocol, ZK rollup, to hop on the Bitcoin bandwagon, as we like to say. Yeah, you can port to Bitcoin in minutes as long as you're already like a ZK rollup. And again, have first-party support for cross-chain interoperability as well. So yeah, if you're building a layer 2, again, my strong pitch is hop on to the L2O bandwagon. We are growing. We support a bunch of different hash functions that you can use for like essentially your cross-chain interoperability. Oh, does someone have their mic on? Maybe give that a mute if you can. 可以关一下，不好意思。好好好。对，然后yeah, so we have a bunch of supported hash functions. So this means that like when you receive a public input to your proof that includes like the superchain state root. So you can imagine that our indexers actually build a Merkle tree with several different hash functions for all of the where the leaves of the Merkle tree contain all of the state roots for the various layer 2s that have deployed with L2O. And that just means that using that public input, your proof can also like read from the state of any other L2O supported blockchain fully trustlessly, which, you know, allows you to do like cross-chain swaps and so on and so forth. Right now, we only support GROS16B and 128, but we're working with some of our L2O partners on supporting more proof types. Of course, if you're using a different proving backend, you can always just write a recursive verifier in a GROS16 proof, and then, you know, verify your proof within a GROS16 proof, and you're ready to go for L2O. But yeah, main idea here is we want to bring like fully trustless apps to Bitcoin, which is what L2O does. So yeah, also is backwards compatible with BRC20. So basically, you can take your BRC20 coins, and the way that you mint these BRC21 coins is just by burning BRC20 coins. That automatically mints you BRC21 coins. And you know, it supports L1 transfers as well, but then I can also lock them in a rollup. And the only way to withdraw from the rollup is providing a Merkle proof that shows that you've burnt them on L2. Yeah, again, if you want to, there's been a lot of talk, shall we say, about the so-called ordinal spam, or lots and lots of BRC20 transactions clogging up the Bitcoin network. Whether you like them or not, L2O essentially provides a way for us to compress all of those. You know, it could even be tens of millions of ordinal transactions into a single succinct, like 300 and so bytes proof, which means like, and again, it has the full same security as, you know, our BRC20 token, but it just reduces the spam quite significantly. So we've actually had some very positive reactions from Bitcoin core developers, despite them not generally supporting more of the other ordinals-based solutions. But yeah, so main idea of how L2O works is you deploy in an ordinal your layer 2 by submitting the verifier data for a zero-knowledge rollup circuit, which is stored by the indexers and is used to verify future proofs that are published. And then after that, you know, as I'm, you know, have users depositing into my layer 2, every time you do it, it like maintains a deposit tree. So when I use the L2 deposit action, it's actually performing an append only operation on this deposits Merkle tree, the root of which is then, you know, passed to your zero knowledge proof as a public input. And when you go ahead and post your block proof, the indexers verify the proof, make sure the public inputs correspond to the like, you know, the actual current state of L2O. So you've got that superchain root that's going to have the state root of all the other L2s, the current L2's start and end state, as well as the deposit and withdrawal tree roots, right? And then when users, or if users want to withdraw from your L2, they just use the L2 withdraw ordinal to, and provide a Merkle proof that just shows that, oh, you know, I have in fact, you know, added this item to the withdrawals tree, and then the indexers check to make sure that the root is correct, verify the Merkle proof, and if it's verified, it then marks that withdrawal is already claimed. So you can't, like, you know, double claim your withdrawals, of course, and then but then it mints you those BRC21 tokens. So end-to-end solution, works with ordinal-based tokens and NFTs, and again, fully backed by proof of math and the security of Bitcoin. So yeah, the only way to compromise an L2O blockchain is if you compromise Bitcoin or the underlying proof system. But yeah, so a few very high, shall we say, very notable partners are omitted from this. We'll be announcing them over the next few weeks. But yeah, if any of you guys are building L2s on Bitcoin, please feel free to contact us on Twitter. I'm at CMPQ. You know, we'd love to bring more minds into the organization, and as we finalize our draft spec for L2OA. But of course, I'm sure there's some of you that aren't interested in, you know, building complex UTXOs on Bitcoin to handle things like trustless peg in and peg out. And you're probably, most of you are also not really interested in building your own protocol. So if you want to build applications on Bitcoin, then QED is a great place to start. So QED is a Palladium on Bitcoin with Web2 UX and scale. I guess this is my pitch part. But yeah, so we're ZKVM agnostic. We support a bunch of different ZKVMs. We also support smart contracts written in like some more traditional languages that have more mature tooling and communities than something like Solidity. But main thing here is we have all of log n block times, and everything is proved end to end. So the only way to publish a transaction on QED is if you have a zero knowledge proof that proves its correct execution, which means that it's mathematically impossible to have invalid transactions on QED without breaking the underlying proof system. So yeah, it's like really fast to use. Again, like we're zkVM agnostic, so we support a bunch of different zkVMs, and you can build really scalable applications. So we achieve this with like fast proof recursion. I guess maybe I've talked too long. What time is it? Shall we first take some more questions if any of them have arisen before we move on? Any questions? Maybe yes, no, maybe so.
Yeah, I have a question.
Sure.
I was wondering, because we only push the proof onto the Bitcoin L1 and verify the proof, and there is only the mock root we can be verified. So how can we derive the mock root, because there is no delay or like zero? Yeah,
oh, sure. So we can go into the specifics. Maybe let me pop open the L2O spec and explain it in more detail. So essentially the way that it works is when you deploy your L2O using L2OA, you indicate what the start state root of your chain is, right? So we basically publish like a zero knowledge proof, or rather the verifier data for some zero knowledge proof, along with the start state root of your layer 2. And then in future blocks, like some of the information you provide includes the start and end state root of your layer 2 for that block. And then all of these guys are hashed up, and we check. So we have a standard for the public inputs to your proof. In fact, it's one public input, which is just the hash of all of this information. And then the indexer itself actually stores what is your like previous state root. So it checks to make sure that that's there. And then for your end state root, you self-report inside that ordinal, but then we hash those values to get the public input and make sure that let's see over here, we check to make sure that in fact like the hash that's your public input is the hash of, I believe, these parameters. Yes. So a single public input, which is the hash that you selected over in when you deployed the layer 2. So if you want to select, for instance, Poseidon Goldilocks for something like a more ZK friendly algebraic hash, you can do that. But we hash the block number of your L2, the current Bitcoin block hash, or actually the Bitcoin block hash as or at the block when you last submitted your proof. So that way you can also trustlessly read information from Bitcoin. And then like a public key, which could be nulled if you want to make like a fully trustless system, or you want to make a system that's, in fact, they're all fully trustless, but if you want to make a system where anyone could submit a block proof as long as it's valid, but maybe you don't want to do that. Yeah, your start and end state root, deposit state root again is maintained by the indexers themselves. So you don't even like need to report it. It just checks to make sure that it's the correct one when computing what that one public input should be. And then again, the start and end withdrawal state roots as well as the super chain root. So the state root, every time a new block is verified, it gets updated in the indexer. So then when you submit another block proof in the future, it checks to make sure that the start state root of the new block proof that's being received is the same as the end state root of the previous block, right? So both blocks are connected back to back. Is that clear? I hope that answers your question. 不知道这个是否回答了你的问题。
Yeah, it's very clear. And I also have another question. Will you post the L2 block data onto BTC L1, or is just stored in the indexers?
So it's stored on BTC L1. So the main thing here is that we want to make it possible for any of these layer 2s or anyone in the world to verify the state of any of these layer 2s just by replaying the Bitcoin blocks, which you can if we post it in an ordinal on Bitcoin. So yes.
Okay, I got it.
So yeah, we can think all of the ordinal spam transactions sitting in the mempool right now, well, so-called spam transactions sitting in the mempool right now could be one ZKP, right?
Hello, I have one question.
Sure.
So I'm thinking like your L2 will have a kind of address, possess all the like deposits of Bitcoin on the mainnet, for example. And then I'm thinking like if someone who have a valid proof to unlock this UTXO, for example, you need to transit from current layer 2 amount distribution to another one. Then indeed, how can you control like the withdrawal is valid? For example, you just unlock this UTXO, it doesn't mean you know how it redistribute the transaction.
That's a great point. So the deposit and withdrawal tree in the L2O spec is for BRC tokens, not for Bitcoin. So QED has our own trustless peg in and peg out for Bitcoin itself, but that's not part of the L2O spec.
Okay, so it's not Bitcoin L2, but for BRC L2.
No, it's on
BRC
Bitcoin. It's just there's not a bridge for Bitcoin as part of the L2O spec. That's a separate set of standards.
Okay.
But just to give you an idea how our trustless bridge works, essentially what you have is you verify a Groth16 proof inside of a tap script, and that Groth16 proof proves that the deposited funds were registered by like the L2, because in the proof, essentially what we can do is we can look, okay, was the transaction that funded this UTXO, does it exist in the transaction history of some Bitcoin that's been replayed to the proof? And then we can look based on like the block difficulty to see, okay, as we're unwrapping the blocks, they need to be padded with zeros, because like that's how you mine a Bitcoin block, right? So you get something like a guarantee that it would be very, very difficult if like there's been, let's say, n blocks since you've reported that, like, you know, that block which contained an ordinal, which had the L2O proof, which had a withdrawals root of such and such, and then we wait n blocks away, let's say 10 blocks. The chances of you finding like the SHA-256 hash collisions for 10 blocks, or maybe you make it 20 confirmations before you can withdraw, is very, very minuscule and would require an enormous amount of power, right? So essentially, if I can prove that there was an L2O, like let's say an L2O block proof that was submitted 10 blocks ago, and that L2O block proof had a withdrawals root of so-and-so, and that there's a Merkle proof that exists which has a Bitcoin withdrawal for me that's of such and such amount, right? Which corresponds to this tap script, which has been funded at this time. And we can see that by, again, looking at the block proofs that have been submitted on L2O before. And then if I can prove, so it is a little bit of complexity there, but if I can prove that that tap script has been funded, and then that tap script's contents is what I'm trying to unlock, then the way that you mint the wrapped Bitcoin is you prove that you've created such a UTXO, which can only be unlocked via the following, or via the aforementioned process that I just went into, right? So like the security, I guess like the security like attack surface is, one, breaking the underlying proof system, two, breaking Bitcoin's proof of work, and three, if you can make a like Bitcoin forked chain that exceeds the number of confirmations that are required for like, you know, by your proof or by your layer 2. So we're probably going to stick somewhere around 10 confirmations, but it also, we may do it depending on like the block difficulty. But we're going to be releasing a white paper that goes into greater detail with that quite soon. Of course, it would be really nice if we just had op CTV, because then, and if we had opcdv and opcat, then we can just make it a recursive covenant. But like, I guess at QED, our sort of like attitude towards like new opcodes is they would be nice to have, but we're not going to be like, I guess, betting on any like new opcodes being enabled. So like all of what we've talked about today works on Bitcoin Core right now. I hope that answers your question, but it is a little bit more complicated because essentially what you're doing is you're verifying Bitcoin within the zero knowledge proof. You're verifying like n blocks of Bitcoin, and you're proving that there's been an L2O block proof which had the certain withdrawals route specifically for BTC, and then you like when I actually go to mint the wrapped Bitcoin on layer 2, I prove that I've funded an address which has that locking script. I guess is like a simplified way of explaining it, but I hope that makes sense.
Okay, I have another question, quick.
Sure.
So you are talking about like you can deposit BRC20 and doing L2 on it. So I think like eventually you withdraw, you need to return the BRC20 to the user. So that means you need to, well, even if it is BRC20, you need to send some Bitcoin from a pool to the user. And according to your description, it seems like the pool should be using some zero knowledge proof verification circuits in the pub script, right? And there should be no typical private key, I think, there. So what about like if someone use like the MEVs to these kind of transactions, they can reuse this script before your transactions and to withdraw all the money, something like that.
No, so to be clear, like the BRC20 solution does not involve like verifying a zero knowledge proof in a tap script. It's providing a zero knowledge proof which is recorded by the tap script. But in order to like actually deposit your BRC20 tokens in, you need to first convert them to BRC21 tokens, because the indexers themselves, like basically there's the only way to like for other than the method that I described before, where we essentially replay Bitcoin inside of a ZKP, and you're verifying the ZKP in like, you know, a Bitcoin UTXO, there's no real way outside of that for Bitcoin to be aware, or for Bitcoin's VM execution to be aware or dependent on like the existence of an ordinal. That's kind of the whole point of ordinals. But you know, to enforce this again, like the logic of BRC20 transfers are enforced by the indexers themselves. So with BRC21, like it has all the same functions as BRC20, except, you know, again, the way to mint BRC21 tokens is you send your BRC21 or you send your BRC20 tokens to like this known burn address. And then when I go to withdraw my tokens from the L2 to Bitcoin, they're not actually held in the UTXO. They're held in the L2, so it's part of the L2's balance of like currently deposited, you know, like coins. And again, the way that you withdraw is you have to provide a Merkle proof that has a root, which is, you know, the current root or the current withdrawals root of the layer 2 in question, if that makes sense. So, and then at that point, you can just do transfers, and the like, you know, the logic is very similar to BRC20. So like when you deposit into a layer 2, those coins are no longer associated with a specific UTXO. They're actually associated with a specific layer 2. Does that make sense?
Okay, so you mean BRC21
so
cannot be like exchange or like trade on the mainnet. It can only be used in L2.
No, you can trade it on the mainnet all you like. So basically the way that it works is we still have transfer, right? It's just that when I deposit into an L2, I no longer have access to those tokens, right? Unless I submit a withdrawal proof on the L2, and that withdrawal gets incorporated into that chain's, that layer 2's withdrawal state root, right? Or that withdrawal tree root. And then once it's in the withdrawal tree root, I can get my tokens back by providing a Merkle proof that shows that I've burned those tokens on L2 and then reclaim them on L1. And then once I've reclaimed them on L1, I can use transfer just like I would with BRC20. Make sense?
Okay, I see. Thank you.
Cool.
So you mean when you deposit your BRC20 token to L2, this BRC20 is burned, and when we withdraw, it's actually BRC21 token.
You got it. And this is because BRC20 has a standard which does not allow you to, it just only allows you to mint and transfer, right? So
okay, so the original BRC20 is burned. You cannot transfer it on mainnet anymore. You can just transfer BRC21
on mainnet.
Okay, I got it.
But it has nothing to do with L2O, right? It has everything to do with the fact that it's not like, oh, the BRC tokens are locked to layer 2s. No, it's just that BRC20 has its logic locked in steel, right? Because this is a standard. So you can't really change it. And this is like I would advocate for BRC21 tokens. There's lots of token standards. The reason why BRC21 is great is because the way that you mint BRC21 tokens is by burning BRC20 tokens. So it's backwards compatible in that sense. And then of course we can do DeFi and whatever you want. So it's basically like BRC like 20 tokens, all the functions of those, and any possible functions that you could possibly desire. You could write a zero knowledge circuit for that logic and then implement your own, L2 or application ZK rollup. And then anyone who has a BRC21 compatible indexer installed, they don't have to install a new indexer for your new DeFi project, right? As long as they have one that can verify zero knowledge proofs with L2O, any custom logic or protocol that you want to, deploy, you don't have to deploy it as a new indexer module. Because there's no world where we have every Bitcoin node running like 500 indexers. No, excuse my language, no effing way, right? Impossible. So how do we get around this? Well, like we need some kind of common execution that everyone can deal with, and we don't want to spam up Bitcoin. So succinct zero knowledge proofs to the rescue, right? It's the last indexer you'll ever have to install. Yeah, because any other application that you would want to build on Bitcoin, you could just deploy as an L2O zero knowledge proof, right? Any other questions?
Hello.
Hello.
Hello. Could you explain the architecture of the global state and the execution layer? What's the interoperation of these two components?
That's a great question. So essentially, the way that it works is we have this thing called superchain state. And the only thing that the indexers store, so this is, again, made for Valladiums, right? So however you want to do your DA is up to the individual L2. However, your state root is stored by the indexers. So for each indexer, it's storing a Merkle tree, which has as the leaves each chain's current state root, right? So we have a tree whose leaves are the roots of your L2's state root. And how you want to actually store your L2 state root is up to you, my friend, right? Now, we do store a deposits tree, right? Which is fine because in order to generate a new data entry in the deposits tree or cause the indexers to store some data, you need to do an expensive Bitcoin, deposit transaction, right? So you can't DOS the nodes by creating those unless you're really, really rich, which is fine, right? If you want to do 1,000 deposits and pay them, a lot of money for it, I don't know what the current mempool fees, mempool that space. Let's see. Yeah, $1.50 per VB if you want to spend, if you're a rich guy and you want to spend a few $10,000, $20,000, $30,000 making lots of deposits, and you want our indexers to store an additional couple thousand bytes, I think that's fine. So yeah.
Okay, thank you.
Any other questions? I think it's not like the success of standards. If you look at standards in the past, it's they need to provide, there's like a few things that make or break them. Is you need to provide like high value proposition for people to adopt the standard. So for instance, this is like the last indexer you'll have to install. You can make any logic you'd like. You can bring L2s to Bitcoin. You can also, any application specific project that was initially going to try to have to make lots of people adopt its own indexer and all that garbage, you now can, do away with by just having a zero knowledge circuit. And again, we're not using any multi-sigs here. None of that centralized mess, right? And then at the same time, we're like, as we try to have as soft of a hand as possible, where leaving the data availability to like the individual L2s, because everyone has their own DA sort of hypothesis right now, but most people agree that ZKP is the safest game in town and Bitcoin is the safest blockchain in town. Any other questions? If any come up, please feel free to shoot me a message on Twitter. I'm at CMPQ. So if you go over here, CMPQ, that's me. Feel free to tweet at me or DM me. I'm usually on here. But yeah, I guess if that's it, then perhaps we shall leave it there. I'm not sure how much time we have, unless there are any other questions.看一下这个聊天室还有没有其他的问题？没有吗？
现在有问题的可以提出来。Carter 中文也很不错，所以大家用中文
说中文也行。
也可以。对。
Okay, well, 就是非常的感谢大家的时间. Thank you guys so much for your time. It's been a pleasure presenting today, and yeah, hope to connect with many of you in the future. And again, I'll put the links for my Twitter and for BitIDE if you guys are curious and want to get into Bitcoin development. So just in order over here, bitide.qeprotocol.com, l2o.io, and of course my Twitter. So thank you guys so much for your time. I think we'll leave it there. Yo-Yo, anything else on your end? I think we're coming towards the end of the hour anyway.
Yeah, we are good. We are good. Thanks so much. Yeah, thanks so much for the sharing today. Yeah, and yeah, we are so happy to have you to give us a talk. Yeah, so thanks for coming to our sharing session today, everyone. Yeah, so it's almost the end, and we will upload the video to our YouTube, and also we'll give the link to you guys. Yeah, and all the sharing can be viewed on our website, Web3BuidlerTech. Yeah, thank you.
Cool. Thanks so much, guys.
Thank you. Right. Have a nice one.
Bye-bye.
Bye.